Right, thank you very much for the introduction. My name is Tom Spink from the University of Edinburgh, and I'm delighted to talk to you about our retargetable system-level DBT hypervisor called Captive. So Captive, this is a high-level overview of how you could imagine Captive from a user's point of view. So there's Captive sitting on top of your operating system, which has to be Linux. You've got your host physical machine, which is where your keyboard is. You've got Linux running, you've got Captive, and Captive provides the illusion of guest virtual machines that are of architectures that are different to the host. So here, our x86 host physical machine is hosting a bunch of guest virtual machines of different architectures. There's an ARM one, there's a MIPS one, and there's a RISC-V one there. And that's what Captive does. It provides that illusion, and it's a full system virtual machine as well. So you can run an unmodified native operating system compiled for that architecture in this virtual machine, and you can run it at near-native performance as well. So let's dig a bit deeper into, well, let's take a look at why you want to use Captive. Architectural exploration, maybe you're interested in developing a new instruction set or a new platform, so you can do that. Instruction set extensions, obviously getting processor IP and modifying them and taping them out or synthesizing them on an FPGA takes time and takes money. But using Captive, you have this ability to rapidly prototype architectural changes. All you do is you modify your architecture description, you give it to Captive, and away you go. You've got a very fast virtualized environment to try out your modifications in. So fast performance modeling, something you can do as well. Captive can emulate hardware processor counters. If you're interested in TLB flushes, instruction cache misses, that sort of stuff, it can emulate those properly. Running unmodified systems, if you want to look at how an existing system works, maybe you've got the firmware from some embedded IoT device that you want to see what's going on with it, you can drop it straight into Captive, provided you've got the right platform description and architecture description, away you go. And yeah, host agnostic virtualization services. You want a virtual machine of a particular architecture, and you don't care what the host architecture is. You can just run it on an ARM server, run it on an x86 server, run it on some architecture you've never even heard of, and you get the virtual machine implementing that architecture. So let's split that first diagram up a bit and actually see where Captive is positioned in all of these things. And it can be quite tricky to get your head around all these different layers and different positions that things are, virtual machines and guest machines. So I'm going to introduce a few terms that are used in the paper and what I'll say throughout the rest of the talk as well. And hopefully bear with me and you'll get what I'm trying to say. So the host physical machine, that is your physical machine. It's exactly as it sounds like. That's your laptop, that's your computer, that's your server. And I'm going to use the examples of x86 and ARM here because that's what we've been working on for the last few years is architectural models for x86 host machines and ARM guest machines. So you've got your physical machine, the big grey box around the outside, running the Linux operating system that has KVM support. We rely on the KVM technology for how the hypervisor works. So you've got Linux with KVM. And then the KVM hypervisor, the hypervisor portion of Captive, runs as a normal application in your operating system. And that's what you interface with when you want to start your virtual machines. You say, Captive, give me an ARM virtual machine. So what Captive then does is it creates what we call a host virtual machine. And that's the native virtual machine that KVM provides that is the same architecture as the host. So the host physical machine, x86, you get a host virtual machine, which is x86 through KVM magic. And then inside the host virtual machine runs the DBT unikernel of Captive. And that's the bit that provides the guest virtual machine, which is the architecture that you're actually after. So you're after an ARMv8 guest virtual machine. The unikernel runs inside the bare metal host virtual machine environment and provides the implementation of ARMv8. So I hope that's clear. And you might be wondering why we actually go to this trouble of implementing a unikernel, because of course it's tricky when you have this bare metal environment, no operating system, no standard libraries, nothing like that. You've got to take care of everything yourself. It turns out there's a number of benefits to doing it in this bare metal environment. And I'm going to explain this one pretty quickly because the paper isn't actually about so much the MMU side of things or what we can do from the architecture and more of the DBT side of things. There is another paper about this. But I think it's useful to know why we actually operate in this sort of way, why we're not just doing it as a host application. So one of the benefits is that we can do MMU page table mapping, which is pretty cool. So ARM guest page table entries semantically quite similar to x86 page table entries. Well, if you're operating in an x86 bare metal environment, you have full control of the page tables. So what we actually do is we take ARM guest page table entries, turn them into corresponding x86 page table entries, and we can use that to accelerate memory accesses in the guest. So we can take a virtual address from the guest system and almost identically replicate it on the host machine by using the hardware page table system, by using the hardware MMU, which has lots of benefits over using a software MMU implementation. Of course, there's little things around that you have to take care of, but it really does accelerate virtual memory virtualization. So this is how Captive works, and there's two stages to it. There's an offline stage and an online stage. And the offline stage is all about producing the architecture module that implements the architecture that you're interested in. So you take an architecture description, which is a file that contains a list of the instructions and how they get decoded, and then a list of behaviors for those instructions. So each instruction has an associated behavior, which is written in a C-like language. I say C-like because it looks a lot like C, but there's extensions, domain-specific extensions that make writing architecture behaviors a bit easier, like rotate operators and various intrinsics. So you take the description, you pop it into GenSim, which is our simulator generator system, which optimizes the model and produces the guest architecture module, which is then used by the hypervisor. So the reason we have this optimizer in this offline stage is so that you can write your architecture description in a really natural way. As a programmer, you might think in the way that the C language works. And if you're writing your architecture description and your instruction behaviors in C, you'd want to use features like function calls and variables and this, that, and the other. So if you can write your architecture description in a very natural way, run it through the optimizer, you're going to get the best performance at the end of the day for the architecture that you're describing. And this is what an instruction description might look like. So this is for the add I instruction, which is add an immediate. You can just see that red pointer there. There's a couple of function calls here that decode part of the instruction to get immediate values and what one of the operands is. And then there's a control flow statements here, which can be evaluated at JIT compilation time to see if it's a flag setting instruction and what size the instruction operands are. And we've got some function calls that compute add with carries, with flags and other things, and then write back into registers. So it's quite a nice way to describe your architecture. And this then gets parsed by GenSim and optimized into a domain-specific SSA form. I'm not going to go through all of this because it's not that interesting, but what you can see is on the left, you get the unoptimized SSA representation of this instruction behavior. Run it through some aggressive optimizations, and you get a much shorter sequence of SSA instructions. And when you have the optimized SSA form of the instruction behavior, you get a generator function. And this is what actually goes into that architecture module. Now, the generator function is generated code, so it looks awful, but it gets the job done. For every SSA statement there, the generator function has an equivalent line in the code to implement that particular SSA operation. And it's this generator function that is invoked by the online runtime every time it encounters an instruction that it has to translate. We typically translate basic blocks of instructions at a time. Sometimes we translate traces of instructions. And for each instruction in that trace, the generator function is invoked at compilation time to build a graph that represents the behavior of that instruction and eventually the behavior of that particular basic block. So taking this guest architecture module, which contains all of these generator functions, we pop it into Captive, into the online stage, into the hypervisor stage, along with your guest system image. So that contains your kernel, and it contains your user space, or any disk images, platform description, what sort of devices exist in the platform. Pop it into Captive, and Captive runs that, and you get your guest machine that is described by the architecture. And this is what the execution loop looks like on a very high level. We start off with the guest physical PC, and the physical PC is checked to see if a translation for that PC exists. And if it does, it just executes the translation and then loops back around. And if it doesn't, the basic block is translated, stored in the cache, and then executed. There's a lot of cool things that we do to make this go faster. So we do jump chaining, and we can stitch things together. But pretty much that's the execution loop. It translates on the fly. And the translation stage is very quick. It has to be to make sure there's not much latency. And the important thing about the PC here is that it is a physical PC, and so we cache the translations by their physical address, which means that we don't have to retranslate when the page tables change. Unlike QEMU, which has to lose all of its translations when the virtual address mappings change. And this is how a basic block actually gets translated. So there's 3 ARM instructions there along the bottom: add x0, x0, #1, mov x1, x0, and branch with link to some address. And what happens is when the translator comes across this first instruction, it produces part of this graph that represents the behavior. So there's a node there which is store, which stores a register, and then there's an addition of a guest register with a constant, and the store goes back into the x0 register there. And then the next instruction is a mov, and the final instruction has a store to the link register and a store to the PC, because we're advancing the program counter by a certain amount. And as we come across nodes in this tree, in this DAG, that have side effects, and we say a side effecty node is one that does something that mutates the guest state, so for example a register write, which is this store here, the tree is collapsed at that point into host machine instructions. So as soon as we come across that store node, we walk that tree and we emit a native code sequence that implements that part of the tree. And when the basic block is translated, we lower that tree, and we get the machine code for the host platform that we're running on. So that add x0 at the top gets loaded to those 3 x86 instructions, the mov, those 2 there, and the branch with link gets loaded to those 3 x86 instructions as we come across each of those side effect nodes in the tree. And we can exploit quite a few architectural features running in this bare metal virtual machine environment. We have full control of the host MMU, which I mentioned at the start. We can use privilege levels, so we've got user mode and kernel mode. ARM have their privilege levels, user mode and kernel mode, and we can mirror that in the execution of our guest and take advantage of memory protections that way. We can use privileged instructions like in and out and syscall and sysret. We can use special registers. We have complete control over the ABI, so we can do things like reserve registers to use for our own purposes. And we can use software and hardware interrupts for fast device communication. And it's fast. Here's SPEC, and there's a noticeable speed up there over everything. The geo mean is just above 2 times. Yeah, it runs at near native speed. Some of our benchmarks that are in the paper show you that it runs about 40% of the speed of a native ARM server, but it can actually outperform Raspberry Pi implementations as well. So that is the end of my talk. I'm absolutely delighted to speak to any of you about any of this in further detail. I've got my poster session later, and I can show a demonstration of it booting Linux if you want to at the poster session as well. So thank you very much.
Thank you. Do you have any questions? Go ahead.
Hi, Keith Winstein, Stanford. That was a great talk. Thank you.
Thank you.
I'm curious, do you think you could run a WebAssembly container with this apparatus?
A WebAssembly container. Well, the Captive is designed to run an operating system. So you take an operating system image and you run it in Captive. So anything you can run inside that operating system, you can run there. That's what it's for. Oh, but I see what you mean. If you wrote an architecture description for WebAssembly, interesting. I don't see why not. If you can write the behavior for the instructions, then yeah, absolutely, you totally could. Yeah.
Did you take the extra step to do multiple cores and SMP support?
Yeah, it's actually something we're working on. So Martin, a PhD student, is working on the multi-core side of things. We've got an initial implementation of it kind of working at the moment. There are a couple of things to iron out, as it is with multi-core, but that is something that we're working on, certainly later this year. We hope to have maybe some papers about that. What we've decided to do is instantiate multiple virtual CPUs with KVM to actually map multiple guest CPUs as well.
Thank you. Fantastic work.
Oh, you're welcome. Thanks.
Thank you. So I have a question along the WebAssembly line. What's that initial effort of getting an architecture specification? I mean, I guess you've gone through a couple of examples. So what does it take to generate those inputs? And is there anything from kind of the traditional architecture community that they already use when they're specifying new hardware that you can leverage as inputs?
Okay, very good question, because the initial effort is extremely high. I've been working on Captive for maybe 5 or 6 years, and that's not just the infrastructure, that's implementing the model as well. So we have an x86 model, but that doesn't have any system support. It just has user support for one of our other simulators. We have an ARMv7 model, which is complete. We have the ARMv8 model, which is complete. And we have a RISC-V model, which is almost system complete, but RISC-V is in a bit of flux at the moment. And implementing a full architecture like that is very time-consuming, and it's taken our team a lot of work to get that over the years to work, because there's writing the instruction behaviors, which can be simple if you're reading from a manual and there's pseudocode available. But then there's also things like the MMU, and there's the devices on the platform that also have to be implemented, the interrupt controller as well. And so that all takes a lot of time. Now, to answer the other part of your question about what is already used in architecture, I know of a couple of things that are used, there's like BlueSpec and there's Sail that have formal descriptions for their models. And I'd really like to use that as a front end to GenSim to take advantage of work that other people have already done, rather than having to use our architecture description language. It's definitely something that we're thinking about. The Sail one in particular, our colleagues over in ARM have the ARMv8 model for that. It's a very different way of thinking to how we've implemented it, because it's more functional, whereas ours is more procedural. But I think it'd be interesting to see if we can reuse those kinds of things as a front end to the simulator generator.
Okay, thank you very much, and congratulations on your award one more time.
Yeah, thank you very much.